interrogate those placements and evaluate the placement's influence on function, including function in energy storage, in catalysis, in fuel cells, and in other applications. David did his undergrad studies at the University of Sydney, if I remember right, in Australia, and actually did his PhD here at Cornell in applied and engineering physics. After the PhD, went on to AT&T Bell Labs and did quite pioneering work at that time, evaluating the limits of semiconductor length scales using some of the very tools that he's now well known for in transmission scanning transmission electron microscopy, STEM. Now he has chosen to tell us work about fuel cell electric vehicles, and we truly look forward to hearing his talk today. So David?
Yeah, thank you. Is there a way to kill this set of lights just over here?
We could try. So I think 5 was the one that worked last time. How about that?
No.
How about that one? Will that work?
That looks pretty good. Yeah. Yeah.
Okay, good.
Is that too dark to video to record?
That's better for us, but maybe not better for
Recording. Try this one. This one, is that one okay?
That's good for me. Yeah.
Okay, so she needs light to record.
Yeah.
And that's the one they told us
Yeah.
to use.
Yeah. Okay. So I'm glad to be here, and the reason I'm talking about fuel cells is it's a technology that makes a difference, and it's one that we at Cornell have an unfair advantage in that we can have a lot of impact in. There's a lot of areas of renewable energy where there's a lot of people working in those areas, and at Cornell, you know, we don't have $100 million of Department of Energy funding for a battery hub, but we can still make a big difference. And so that's what has attracted me about this technology. It is in some sense a competitor sort of to batteries. I'll talk about where batteries do well and where the fuel cell electric vehicles do well. But it's one that we can see, and we've already seen in the time I've worked with companies like GM, the changes that have happened. So this picture over here is, in fact, this is the Toyota Mirai fuel cell electric vehicle, sighted in the wild by my student Elliot on his honeymoon, oddly enough. And so this is a fuel cell electric vehicle. It's being sold commercially in California. And Elliot has, in fact, looked at what this particular fuel cell looks like. Not this car because the owner bought it, but this is a piece of a Mirai fuel cell that Elliot has looked at. And so when he saw one out in the wild, he ran out and took a picture of it. That was, I think, very satisfying. So very briefly, as a consumer or a customer, what a fuel cell electric vehicle is an electric vehicle that is long range, and you can charge it up and refill it in about 5 minutes. And those are obviously two weaknesses for battery electric vehicles. If you're an engineer, what a fuel cell is it's an engine that is going to produce electricity by oxidizing a fuel. And the fuel that we tend to be interested in is hydrogen. That if I take hydrogen and I mix it with oxygen and form water, I'm going to get 1.23 electron volts for every time I do that. And then the trick is normally I would do that by the little Hindenburg demo you get in freshman chemistry, where we take the oxygen and the hydrogen, mix them together, and go boom. And by the way, the word rolling Hindenburg is forbidden at GM. It's on their list of forbidden words. We'll come back to why you don't have to worry about that. But the idea of the fuel cell, as with many of these electrochemical reactions, is if you split the reaction into half reactions, which you're used to doing formally, but if you actually build a cell that does that, you're going to make that electron that you want to do work go through an external circuit and combine it with the ions that go through the inside of the device. And that way, I've taken a chemical fuel, I have produced an electrical current that I can do work with, and these turn out to be much more efficient than trying to build a heat engine and relying on the Carnot cycle. We'll go into that in some detail. In many cases, 2 to 3 times more efficient than if you just burnt the fuel and try to run an engine with it. Now, the challenges in building a fuel cell are you obviously need an electrolyte, which is going to let ions through, but not electrons. And the electrolyte also has to make sure that the fuel just doesn't leak through, that my H2 gas doesn't get across to the other side, because then I can't make my electrons go out and do some external work. So as a practical detail, that's our cartoon of a fuel cell. And there are many different types, and we're going to pick a couple that we like. And I should point out that my group got dragged into fuel cell work over a decade ago because GM used to have its secret fuel cell development plant in Honey Eye Falls, which is about an hour-and-a-half drive from here. And the directions to how we got to see their secret fuel cell plant was literally you turn right at the barn and you make a left at the horse feed store and go past the hedge, and there's a security guard and a gate behind the hedge. And I still have the email with those kind of directions. I wanted it in a very out-of-the-way, quiet place. And then in 2008, when GM was sort of consolidating and contracting, they moved all these folks out to Warren, Michigan. And I think you've got Mark Matthias scheduled to talk. Mark was the director of the secret fuel cell project. And so we got out. They had trouble understanding what was happening with their catalysts and their supports and why they were degrading. And so they came to us for our electron microscopy skills to take a look at what was going on. And so here's an earlier generation of students over there. And we all went out to GM and we drove their Chevy Equinox fuel cell vehicles. So they've had test vehicles in upstate New York for well over a decade. And we had great fun driving this at high speeds on back roads. And these two folks have gone on and are both a faculty at Harvard and at UC Irvine, and Randy now works for Facebook. So a little bit of history more broadly about fuel cells is Grove was the first person to describe a fuel cell where combining the hydrogen and oxygen in the right way, you got a small electric current. When you see his cartoon of what was going on, it was incredibly inefficient, and you can understand why. And it basically didn't have that very nice electrolyte set up efficiently. The first practical fuel cell was Francis Bacon, and by the 1950s, his alkaline fuel cells were producing 5-kilowatt power plants. And these alkaline fuel cells are both some of the earliest and some of the most efficient. By the 1960s, GE had taken these alkaline fuel cells and were using them as power plants on the Apollo missions and the Gemini missions. And here's an actual picture of the fuel cell from the Apollo service modules. And they played an important role in the Apollo 13 mission. So those are the first. They have a weakness to them we'll touch on, which is they don't like working with air. They prefer working with oxygen. So along the way, people then developed other types of fuel cells. The solid oxide fuel cells are very useful for power, stationary applications, and in fact also things like buses, because they run all day, and these like to work at very high temperatures. And they're also looking quite useful for marine applications. Diesel engines are incredibly polluting, and you can get in mid-scale vessels and submarines, the fuel cells can be extremely efficient and use your fuel much more effectively than you would otherwise. Key development for the automotive industry was DuPont developed Nafion, and they found that Nafion was a very good electrolyte membrane. It's extremely insulating. It's very inert. It's basically glorified Teflon with holes in it. And that was a great electrolyte for proton exchange membrane fuel cells. And that led to a lot of demonstration vehicles using hydrogen-air proton exchange membrane fuel cells. And that, for the automotive industry, is the main technology. Now, the challenge of why did it take this long before you had something that looked interesting? There were several issues you had to worry about, and this cartoon sort of captures the engineering challenges of this problem. what I'm trying to do is I want to bring in my fuel. I have to bring in the thing I'm going to react it with on the other side. My reaction, particularly splitting up the oxygen, is a reaction which really doesn't want to happen. And as a result, the overpotential for that, you need about 400 millivolts to get that going. Otherwise, it's just too slow. So you need a catalyst. And you're trying to work at a triple point of where things are happening is I have to have my gas molecule, I have to split it up on the catalyst. I have to now persuade the electrons to go one way and the ions to go another way. And so the design of that membrane is a very challenging problem, and it spans many length scales from how do I get to diffuse the gas uniformly over the catalyst material, how do I get to separate my charges in ways that I can run the one through the external circuit and then the other one through my membrane. And the catalysts themselves are nanoparticles that are most efficient if they were all surface area and no volume, because reactions happen at surfaces and not on the inside. So my catalysts themselves, I want them to be really tiny. If they were single atoms, they'd just move around and they'd diffuse and I'd lose them all. So there's all sorts of stability and durability challenges that we face in designing these sort of things. Now, it's worth noting that there actually are several commercial fuel cell electric vehicles on the road already. Toyota has their Mirai fuel cell vehicle. I think it sells for a little over $50K. You can buy it in California and perhaps down in New York City. Hyundai has one and Honda has one. I think the Honda one you can lease. They're a little nervous about the long-time stability and durability of the catalysts. Toyota is pretty gung-ho about it. And the reason for that, in fact, is they just loaded up way more catalyst in there than the other guys did. There's about $1,000 of platinum sitting inside a Mirai fuel cell. And we know that because we've chopped one up and taken a look. So early adopters, GM, who we've been working with for over a decade, keeps insisting that their fuel cell vehicle will be on the roads commercially in 2 years. And they've been saying that for over a decade. So they have demo vehicles. It's a question, it works. There's a question of either the catalyst is not going to last the 10 to 12 years you'd like in a car, or I have to put too much of it in to make sure there's still some left at the end of life. So that's the challenge we're going to talk about, is really, as with all engineering problems, it comes down to, in the end of the day, it's always cost. And that's an important thing to remember if you're not an engineer. So a little bit about, just very quickly reminding you, some of your freshman thermo, the definitions of enthalpy and my Gibbs free energy. Right, the Gibbs free energy is the net energy cost for the system less what's supplied to the environment. The fuel cells are often run at constant temperature and pressure, which means the maximum electrical work I'm going to get out of a fuel cell is going to be my Gibbs free energy. So if you ask about, okay, how much energy am I going to get out? The efficiency of the system is the energy I put in is going to be my enthalpy. And that depends whether I'm starting with a liquid, water, or at least finishing up with a liquid, water, or a gas. So the temperature is going to make a small difference. It's not a big change. But the efficiency, the best I hope to do out of a fuel cell in efficiency is the work done out of the total energy I put in. And that's the Gibbs free energy over the enthalpy.
David, just one point about efficiency. So there's another kind of efficiency that we like to use, which is the actual work over the real work.
Right.
So
yeah.
what, you know,
so I'll come to. Yeah. So this is our upper limit. I want to use this to benchmark because this is not a Cornell engine, right? Right. So it's going to behave very differently to a Cornell cycle. We're then going to take another look at where are all the other loss mechanisms that happen along the way. But if you're a chemist and you're funded by NSF, basically I'll show you on a plot of, you know, where we are and why this is only half the story. So here's basically what I was leading up to. And the main thing I wanted to point here is, you know, hydrogen is a good fuel, so why not just burn hydrogen, right? You burn the hydrogen in air, you get water vapor out, and that's a perfectly good engine. And I could make a hydrogen-powered internal combustion engine. And the answer is, of course, the best I could ever hope to do, and I'll have a really slow engine if I did, would be my Cornell efficiency. And the fuel cells are playing a different game. And of course, Cornell is woefully optimistic. Normally, I'm going to be using something like an Otto cycle. And there are a couple of constraints that are going to be placed on my internal combustion engine. Obviously, I'm going to do better at high temperature, but at some point, my engine melts. And that means sort of, I'm never going to run it at that point, but that's going to stop me about 37%. And my typical efficiencies are 15 to 20% for the internal combustion engines. Whereas the best I could hope to do for a fuel cell is going to be around about 80%. We typically run the automotive fuel cells down in that range around about a little bit below 100. Now, in reality, we'll see you don't actually get there, but the alkaline fuel cells will make it to 70%, and some of the other ones are sitting around about 60%. And that's still way, way better than what I could hope to do with the Carnot cycle up around there, right? And think about even 60% compared to 20. Obviously, diesel engines do a little bit better, but they have a bad name right now thanks to Volkswagen. So the next thing to sort of think about is the energy densities of the fuel, right? How much fuel do I have to carry with me? And hydrogen is an incredibly efficient fuel if you look at it by mass, right? And I'm taking in the oxygen from outside, and well, that's free and available. That's great, but in terms of volumetric densities, it's not particularly efficient as a volumetric density, right? So you got to think, yeah. So you got to think about these sort of things where you want to deploy this. Hydrogen-powered aircraft is going to be a little bit of a problem because you don't have a huge amount of room to store all that hydrogen. Car, we're actually not too badly off, it turns out. It's worth remembering that our good old-fashioned internal combustion engines are sitting out here, and in terms of, they're pretty good energy densities and they're pretty good volumetric densities. The things that we're really comparing to, of course, are things like, how's a lithium-ion battery doing? Right? That in many cases, that's our direct competition. And compared to a lithium-ion battery, we look pretty darn good. We've certainly, most of the vehicles are using compressed hydrogen gas, so much better volumetric density than trying to put batteries in the vehicle. And then just a reminder about energy densities is TNT, there in fact was a very early proposal, very early designed vehicle in the late 1800s that ran on explosives. Many drawbacks. Just a reminder that TNT doesn't have great energy density. It has very good power density. Right.
So David, a quick question about metals. So what is it you have in mind? So the metal going to being oxidized? Is that
exactly, yeah.
Getting the cathode?
Right, okay. Yeah. So, obviously zinc, and there's, the whole zinc air system. And so, so, that sort of, when you're thinking about things, it's, I'm going to be more bulky than I would with that, but in terms of weight cost, it's going to be less. Now, the other way you sort of compare these the different technologies is you care about power density as well as energy density, right? So the way to think of it is your energy density is going to give you range. The more stuff you can pack in the vehicle, the further you're going to travel. The power density is if I put my foot in the accelerator, can I supply enough power to keep me happy? And this is, I think this one is Tito's review article. Do you remember which picture you recognize? One of those.
A well-known one.
Yes, yeah. The lesson is the internal combustion engine, your gas turbines, have good performance on both of these metrics. The fuel cells do really well in terms of range compared to batteries, but they don't supply power necessarily as fast as you'd like. And so usually what happens is we supplement them with a supercap. when you need the acceleration. And if you think about it, the supercaps, you know, the range of the fuel cell will do just fine compared to the internal combustion engines, and the supercap will get you the power you need. And so you now get to replace all the components you need for a car like that. This one seems to, you know, in fact, battery electric vehicles often have a supercap stuck in them as well for when you decide you want to do 0 to 60 in under three seconds in your Tesla. Which is, of course, another advantage of electric motors is incredible torque when you start out. So if you want a sporty car to take off from your traffic light and make everyone else look silly, electric motors are the way to go. Top speed, and then of course just reminding you, TNT has much higher power density and acceleration than petroleum. Now, the weakness of electric cars is more or less captured in this plot over here, which is a plot of all the electric vehicles on the road, what was their range, and what was their battery capacity. And you see more or less the only thing you need to know, almost, to know the range of an electric vehicle is how big was the battery, more or less. There are subtle variations of a few percent. The new vehicles seem to be doing a little bit better because the other parts of the system are optimized. But really, the drag coefficients, we've optimized it as much as we can unless you're willing to drive lying down. So this is sort of where we are. Now, if you're a chemist, and someone told you what the battery capacity was in kilowatt hours, you can actually go look up from the materials the battery is made from, and you're going to know how big and heavy that battery is, and you can go look on Alibaba and figure out how much the components of that thing cost. And what you'll sort of very quickly find out today is your 100 kilowatt hours that you would have in a Tesla S, that's about $27,000 of battery pack for this guy. Now, it also, when you figure out kilowatt hours and you know the potential for the chemistry of the battery, you're also driving around on about half a ton of rocks. So that's a real big challenge. Now, if I want to do better for electric vehicles, and I want to think about, okay, I need a cheaper chemistry. Cobalt's pretty expensive. The lithium is not particularly expensive. The electrolytes are sort of somewhere in the middle, but it's still not the major cost compared to the transition metal you have to do in the battery. And the cheapest one we can imagine, if you did maybe a manganese chemistry, your lithium-ion battery, you'd be looking at about $13,000, and we certainly can optimize it, you know, below what this cost. And in fact, Tesla's even got that cost down since then. But about the cheapest your battery is going to be is about $13,000, and that's the cost of a entry-level internal combustion engine. If you want to make an electric vehicle that will make gasoline engines obsolete, whatever you're using for your energy delivery system, it's got to be between $1,000 to $3,000. That's basically what your engine and transmission is going to cost in an entry-level vehicle. If you're trying to do it with batteries, you've got to find materials at below $33 per kilowatt hour. And there are materials that will do that. Sulfur, for instance, is dirt cheap, but they're not particularly stable. So there's a challenge of trying to come up with batteries that can be for everyone, that get you a range that Americans would be happy with. Europeans would be happier with the lower ranges, for instance. Their countries are much smaller. But any new technology, you've got to be in that kind of range. And that's why I mentioned the $1,000 worth of catalyst in the Mirai fuel cell. It's got to come down. But obviously, the rest of the fuel cell's got to come down in cost as well. So a little bit of, you know, if I start to plot out cost of vehicles versus price, and start to think about how do I bring things down, right? There's a big chunk of this that's just the battery. And this is sort of telling you how much Tesla is selling a car without an engine in it for. You know, if I can bring the, and then just the cost of the lithium ion cobalt is sorry, the nickel, the NCA is about that. The cheapest I might imagine is something around that. So if I try to do a base entry level vehicle, I got to kind of bring things, you know, if I do that, my cheapest gasoline vehicle is double the cost of what an internal combustion engine is right now.
So what about the new Tesla that's not $80,000 for sure?
Right, right. So that's,
And the
yeah.
range of that is comparable.
It's coming very close, yeah. And then the question is,
Down significantly on
yeah, let me, it's, I put it, yeah, so it's this guy over here. It's almost making the range. The battery pack is smaller, and it's sitting at about 40K these days, right?
So that's a big improvement.
Yeah, so that is a big improvement. And again, right, if you look at that there, you've probably got that much battery, right? So, you know, the Model S is a 40K car without an engine in it, and the Model 3 is about a 25K car without an engine in it, is the way to think of that one there. So, you know, you can imagine, you know, the best case we're going to do is I'm going to cut the cost of a Model 3 by a factor of 2. Which is okay, but you're not going to get everyone to adopt it because that's still twice as expensive as sort of entry-level base models. That's kind of what I'm trying to think about over here. That you really want to sort of be setting something that looks like that, right? That's what the cost of the engine is. That's the cost of the car without the engine. And I want to kind of get myself in that range. Because if I can do this, then there's no excuse for having an internal combustion engine ever again. You have something that's higher maintenance. You have something that's less efficient. You have something that, you know, you have to take to the dealer to get the oil changed. And if I get my electric vehicle in this range here, I have something that's sportier and zippier with the same range, lower running cost, and the same purchase cost. At that point, all of that oil in the ground is obsolete. So that's sort of a long-term goal, you know, I want us to think about. Because if you can do this, then you don't, you know, if you have to legislate for people in you know, who live on a farm with a pickup truck, that they have to give up their truck. You know, if you think they're touchy about guns, wait till you hear how touchy people are going to be about their cars. Right? That is a societal issue, is a real big challenge. So now, what do we do about fuel cell vehicles? Here's the Mirai today on this plot. And what I've drawn over here in this very narrow box is basically what would the cost look like for the Mirai if I changed the range of the vehicle. It turns out that hydrogen storage on the scale of batteries is very cheap. It's sort of roughly a $7 per kilowatt hour. Remember, the $33 per kilowatt hour was sort of that difference there. Hydrogen storage is about $7 per kilowatt hour. The size of your hydrogen tank is independent, well, at least the cost of the amount of material you need for a hydrogen storage tank is more or less independent. It's, you know, the amount of material per kilogram of hydrogen is independent of the size of the thing. So when I make it twice the size, it's twice the cost. It scales, and the scaling cost is not particularly big. The problem right now is this is the cost of the fuel cell. Right? That the fuel cell is, the way to think of the competition between an all-electric vehicle and a hydrogen fuel cell vehicle is the obvious point is that if the vehicle is, if you don't want a lot of range, batteries will always win. If I want a very long range, the hydrogen fuel cell will always win. But obviously, if the engine is this expensive, I've got to get to ridiculously long ranges before I make that crossover. And so the key is, can we bring the cost of the fuel cell down? Now, most of this cost is these things are being hand-built. They're not being mass-produced. So you can expect a lot of that to come down just as you scale up production. But there's definitely a lot of fancy and expensive parts in a fuel cell that we want to greatly reduce the cost on. And if you can do that, and if you look at what the parts cost, these things shouldn't really be much more expensive than your catalytic converter. That's the end goal, is have no more platinum in the fuel cell than you have in your catalytic converter. Every car has a catalytic converter. You ought to be able to get down to those ranges. And at that point, this thing becomes cheap enough that unless I'm talking about maybe 20 miles of travel, the fuel cell electric vehicle can potentially be competitive. It has a second advantage, which is because I'm fueling with a solid fuel, I can fuel up the car in under 5 minutes. And people have built very nice fueling stations to do that. Whereas the electric vehicles, charging is a real problem. Normally you want to charge overnight. If you charge rapidly, you can do horrible things to the life of that battery. So what are the technologies available to us? The one we're focusing on is the PEM, the proton exchange membrane fuel cell. It has a solid membrane, usually Nafion. It's taking in hydrogen as a gas. It's bringing in oxygen or atmosphere, either is just fine. You're running at fairly low temperatures, and the efficiencies are usually, these days, more to around the upper limit. They're around about 60%. So you're looking at maybe a 2 to 3 efficiency improvement over an internal combustion engine. The earliest type of fuel cells I mentioned were these alkaline fuel cells. They can have efficiencies up to 70%. Their traditional weakness, I'm going to come back to this, was they used potassium hydroxide as an electrolyte. And the problem with potassium hydroxide is if you encounters air and you get some CO2 in there, you're going to form carbonates and the whole thing is going to clog up. So they had to run with pure oxygen. I'm going to talk later about ways to get around this problem and take advantage of this better technology. There are other technologies that pop up. The methanol fuel cells have been proposed for electronics because you can make them very compact and they can operate at conveniently low temperatures. Problem is methanol is poisonous, so not necessarily clear you want to be filling up your computer with the methanol. On the other hand, these little methanol fuel cells have demonstrated, like, a cell phone that lasts a week without having to charge, and laptops that can last a week. There are some promising intermediate temperature technologies. They run a little too high for cars, which you're going to turn on and off fairly regularly, but probably more interesting for things like buses and small power that is, at a company. Solid oxide fuel cells are popular for mid-scale power generation, businesses, and running buses. They run hot so that you need to keep them on all the time. Okay, so the PEM fuel cell is the one is one of the two I'm interested in today. Reminding you again, the key to this thing is I need to get my protons across a membrane that is electrically insulating. That membrane is usually Nafion. Conductivity is a 0.1 Siemens per centimeter, and it does depend on the relative humidity. So you've got to watch how much water is in your fuel cell. And conductivity gets better at higher temperatures. We're usually running at about 80 to 120 degrees C. Good power density. Problem is the oxygen reduction reaction. This is the oxygen plus protons plus electrons and assembling that to form water. This is a lot of things to dance and juggle all at the same time. And so this is a very, very sluggish reaction, and this needs a catalyst. And that catalyst usually needs a very expensive element in it. I think Tito will call this is...
God's collective punishment to electrochemistry.
So here is what a fuel cell vehicle looks like. This is the Chevy Equinox. There's your hydrogen tanks. They're usually either stainless steel or Kevlar. And the Daimler-Benz people have explained very patiently how they've tested these things. You cannot penetrate the Kevlar with a handgun. And if you hit it with AR-15, it makes a nice clean hole. The hydrogen diffuses out very quickly. And it's gone. You can't actually, it doesn't stick around to cause a fire. But they've tested those things. I guess that's for the American market. Well, we'll come back to the safety issues there. It's surprisingly, it does better than you'd expect. So the fuel cell itself is, each time I do this reaction, I get myself 1.23 volts and a certain amount of current based on the amount of fuel I put in. So you end up arranging not just one cell, but a whole stack of cells, so you can add them up and get a nice voltage out of that. And the cell is built, I'm sorry, the picture's a little darker than I would like here. But what you're trying to do is you're bringing the hydrogen in from the one side, the air in from the other side. You diffuse it through a gas diffusion layer into your cathode. Your cathode is the spongy looking material. It has to be porous so you can get gas into it. And then on that spongy porous material, when I get down to the scale of nanometers, the spongy backbone, which has to be conducting, is covered with a little catalyst material, which are nanoparticles, just a few nanometers in size. The reaction happens at the nanoparticle. Then I have the challenge of persuading the electrons to go out through the conducting carbon to my external circuit, persuading the ions to go through a ionomer layer, which is a coating of a few nanometers of ion conductor on the surface, which will make contact with the membrane, through the membrane and out the other side to reassemble the protons plus the electrons, mix them with oxygen, complete the electrical circuit, and your waste product is water coming out your tailpipe. So it's a clean technology provided your hydrogen is clean. So now we get to the practicalities of the system. This is sort of what Jeff was talking about, that my theoretical efficiency over here is, I'm expecting 1.23 volts. I'm ending up with 0.95 volts under the condition that I don't move any ions around. So that's my open circuit voltage. Now, when I try to move the ions through that electrolyte, that is it has to conduct. Therefore, it has a resistance. Therefore, there is a power loss. And so there is going to be losses of efficiency, V equals IR. And so when I start to think about the drop in potential, as I start to draw current, the fact that I have a resistance in my circuit, because my conductivity is not perfect, means that my voltage will drop. The power I generate, P equals VI. So it's the most power I'm going to get is I want to go to a big current, but I also want a large voltage. And so this curve actually has an optimum where I'm going to want to operate if I'm trying to draw the most power most efficiently. But it turns out, that points out here, the trouble is I also generate a lot of heat in the system. And generally I want to sort of just stay above, my limit of where I want to get to is usually about 0.65, 0.55 volts, somewhere in this range. Otherwise I'm really just dumping too much heat into things. So as I go down here, I have two loss mechanisms. I have my ohmic losses, which is the conductivity. And then I have a mass transport problem, which is, am I efficiently getting all my oxygen in and out? Am I using it all? And can I get everything in and out of the catalyst? So I have to make sure my gas flow is properly engineered. And that is going to set the ultimate efficiency of the system. And you can kind of very quickly squint and look at things here. And remember, 1.23 volts would be ideal. And if I'm at 0.6, I'm down about 50% efficient, which is still way better than what I'm going to be getting in the automotive, in the internal combustion engine. And my electric motor is about 97% efficient. So, this is where most of my losses are happening. So, if I have the right catalyst, I get to play with this point over here. And this is basically what NSF will fund chemists to do. And everything from here on out is what they'll fund chemical engineers to do. So, here, our first hit we take is this overpotential because of the poor kinetics. So, and then we lose another 12% from the ohmic losses. So engineering this part is just as important as designing a good catalyst. So how much time do I have, Lyndon?
Probably about 5-ish with questions.
Okay. Yeah. So very quickly, the things I want to highlight are the catalyst itself can be engineered by playing with the chemistry. And what you're actually doing is the surface of these materials, it's not showing up very well here. The surface of these catalysts, they're just a few atoms in size, is always platinum. But the other material you're alloying it with is changing the lattice constant of the platinum, which is changing the D-band center, and that's driving the efficiency. So we've developed some catalysts at Cornell that have very good efficiency, and doing it by engineering the structure of the core of the material to make it more mechanically stable. I'm going to skip through a major challenge with the vehicles is when you run these catalysts, they degrade. The catalyst that's trying to reduce oxygen is in a very, very strange state. And what happens is you start to pull atoms off these catalyst materials. These things run around, they bump on the surface, they coalesce. And when they coalesce, I now have a smaller surface area. And as a result, my activity drops. There's a whole bunch of degradation mechanisms you have to worry about. Here is the performance of the cell. You can see it takes really big hits as a functional lifetime. And I have two different structures over here, one where the catalysts are inside the support and protected, the other one where they're outside and they get to move around and degrade much faster. So there's a lot of engineering you get to do with the transport flow. And let me just skip through. This is just showing you two different catalysts, one where they're all on the surface, the other one where they're on the inside. The stuff on the surface degrades really quickly. The stuff on the inside survives pretty well. So you get to end of life. My particles are smaller. This one, everything's big. It's really lost a huge amount of its efficiency. The next type of fuel cell I want to talk about, this is what I want to advertise at Cornell in the last few minutes, are what are called alkaline fuel cells. Normally they don't work because if I've got potassium hydroxide as my electrolyte, add CO2 to that, I get clogged up with carbonates. So I need a magic membrane, which is called an anion exchange membrane, which will let the OHs through without getting chewed up by hydroxyl groups. And it will block all of the CO2 flowing through, so I'm not going to form carbonates. So if we can do that, we have a much more efficient fuel cell that also doesn't require platinum, because the reaction kinetics are different, and I don't need the platinum catalyst anymore. So at Cornell, we've just started a Energy Frontier Research Center, $10 million over the next 4 years. Most of that money is going to fund students. So people are looking for students in the center, and the goal is to study what is it going to take all of the aspects of the technology required to getting alkaline fuel cells to work. Durability, cost efficiency, the catalyst, the membrane, and how do these things degrade. So these are the faculty involved in the center from all over the university: chemistry, material science, chemical engineering, and we've got folks from outside the university as well. So the two magic things we need to make a successful alkaline fuel cell is we need the alkaline exchange membrane. Jeff Coates' group has found one that appears to look very promising, and we just now we need to tweak and optimize on that. And you need a catalyst that works in an alkaline environment, and you'd like it to outperform platinum, and there are many candidates that look like they're coming quite close. These are some spinels from Yao and Tito Abrunha's group, and that's what the structure of a spinel is that Yao took. So last thing I want to sort of touch on in the last few minutes is the obvious fear everyone has about hydrogen fuel cell vehicles. You're driving around on a tank of hydrogen. So here is a DOE test of let's blow up a hydrogen fuel cell vehicle and let's blow up a normal car. Let's set fire to their gas tanks and ask what happens. Turns out, here we are 3 seconds into the ignition. There's the hydrogen venting out the back of the car, and here is the fuel starting to burn. Hydrogen is the fastest diffusing, almost the fastest. I think it's faster than helium, but I don't remember. It's faster than helium? Yeah. So it diffuses so quickly it cannot be contained. It goes up and out and it's gone. So a minute later, there's still a little bit of hydrogen venting from the tank, but all of the liquid gasoline has pooled in the vehicle and poured all over the driver and burned them to a crisp. Here we are a little bit later on. What you're not seeing effectively is the entire car has burnt to a crisp with the driver inside. And for the gasoline vehicle, hydrogen vehicle, everything is intact because it's venting outside. So it's very hard to get an explosion going, and it's very hard to get it to burn the rest of the vehicle, which, you know, the thing to remember is hydrogen is dangerous, but anything with that energy density, right, if you're storing 100 kilowatt hours of energy in your car and you let it all go all at once, that's a big bang. So it doesn't matter, batteries at that much energy in batteries are also dangerous. And it's a question of how you discharge it. And so, you know, again, you can be careful with how you discharge the battery. We've obviously had 60 years to try and make gasoline fuel tanks safer. The last kind of reminder is, you know, how do we produce hydrogen? Because if I produce hydrogen in a clean fashion, I have a greenhouse gas friendly clean vehicle. If I produce hydrogen in a dirty fashion, I have a contributor to carbon emissions. If I produce hydrogen from coal, which is a cheap way to do it, I have a problem. This is taking natural gas, producing hydrogen. This is dirty. If I can do electrolysis or photocatalysis from water, split water using electricity, this is very clean. And one of the advantages is you can imagine running solar cells during the day. You use your excess capacity during the day to produce hydrogen, and then you transport that and use it as a fuel. It's a very efficient storage, and it solves the storage problem you have because batteries right now are very expensive compared to trying to do electrolysis. The hydrogen generation, there's a hydrogen fueling network in California. It's using the Nel hydrogen electrolyzers, so they're supplying electricity, hopefully from their big gigawatt photovoltaic plants, and using it to generate hydrogen, and the cost is between $6 to $12 per kilogram, which is sort of basically, think of it as a cost of about, you know, $5 to $10 per gallon if it was fuel. That's your competitive cost where we are now. So just wrapping up again, 3 vehicles on the market today. Ranges and performance are very comparable to the internal combustion engines. So very quick to refill and comparable ranges. So with that, I just want to wrap up reminding you we have a center looking at alkaline fuel cells, which would be one way to dramatically reduce the cost of the fuel cell. Our challenges are cost and durability. You can trade one off for the other by lumping more catalyst in there. And then just for my group, an acknowledgement of folks we've worked with over the years. Obviously Tito's group a lot, and theory work with Tomas Arias, and some of the microscopy and tomography with Lena, who is now faculty at Cornell. So with that, I will stop and wrap up.
We've got time for about 4 questions. To the safety video that you showed, I mean, this is it's sort of a generic challenge, because I think if you were to do the same experiment in a battery-powered car,
Yeah.
and a internal combustion engine-driven car, you'll find more or less the same result. I mean, you
Right.
have the same details.
Yeah.
But society never listens in that way, right? So I think that kind of demonstration only has a certain degree of credibility, in part because, as you said, we've just figured out how to make internal combustion engine cars safer, and we don't have as many constraints and the conditions that were used in the assessment, and whether those constraints could actually be implemented at commercial scale.
So along these lines, David, and thank you for this very interesting talk, but the infrastructure to deliver hydrogen at scale and at high pressure is not trivial. And we can take your first demonstration I saw of a Toyota fuel cell vehicle drove across the U.S. It had following behind it a high-pressure hydrogen tanker truck, because there was no hydrogen refueling. And
Right.
plus, refueling is a big deal for people because they love to pull up to their
Yeah,
service
yes.
station, fill up the tank, while smoking a cigar or
Right,
cigarette.
right, yeah.
And it could be inherently dangerous if you're talking about hydrogen that way. So
Right.
do you have optimism?
Yes, yeah. So it's I don't have the slide with me. I can pull that from my other notes. You can imagine people have put a lot of effort in thinking about this,
Sure, of
right?
course.
And the current hydrogen fueling things look like gasoline fueling things. They've actually made it look like the little gasoline handle. It plugs onto a nozzle on the car. It clicks into place so you make sure you've got a good connection, and then it pumps the hydrogen in, and it'll do it in 3 to 5 minutes. So it feels like you're filling up your car at a gas station. And they've gone to a lot of trouble to design these things to look exactly like gas stations. Now the question is, how do you supply the hydrogen to the gas station, right? Because you've got to build out the whole infrastructure.
What's
So
the pressure going into these tanks?
I think I'm remembering it's a 70 megapascal, right?
So that's
Yeah.
700 atmospheres, just to put it on that scale.
Yeah. So
So the other potential safety issue could be explosion without fire, and then the compressive energy in those tanks is significant. So if it
Right.
lets go, you can kill some people in that car quite easily without any fire at all.
right. I mean, this is it's the
That's a big
same.
deal.
We're used to those compressed gas
Exactly.
technologies, right? We know about them from all the safety in the lab and how to secure them. So I mean, the tanks are sort of they try to design these things so that you can blow off quickly without it shooting the tank as a torpedo, right? Those are definitely that's a sort of the GM. So those are things that's nice. That's why I like when GM and Mercedes and Daimler-Benz do this rather than a startup, because the startups take shortcuts. These guys don't, because they know that if they get sued, you've got money to recover from them. So the thing I want to sort of say about the hydrogen networks, there's a couple of ways you deliver hydrogen. The GM strategy, they actually have the the demo system is in Hawaii, because you only have to put one fueling station on the main island and you can always drive back to it. And the GM strategy was you actually put hydrogen in natural gas lines to improve the flow. And so they basically just tap into the natural gas line and let the hydrogen, which diffuses much more easily, pull that out the natural gas line, and the little parasite tapping onto the side of that, and that's the hydrogen that they then sort of pump up and pump into your car. The other design are the electrolyzers, and that's sort of the Bob Shaw network, and those look like a container from that you put on a truck, and you dump that in your Walmart parking lot. You plug it into the wall to get electricity, and you're good to go, and everyone comes in and fills up. So that's a install it as you go kind of thing. And then the idea is to try to put those out at scale. So it's surprising to see how quick the hydrogen network has gone in California. It's very much a chicken and egg thing, because if you don't have lots of cars, how do you make money with a hydrogen fueling station? So that, in some sense, that's the big weakness, is how do you build out that infrastructure? Speaking to one of my friends in Germany who does electrochemistry and is very much a fanatic for hydrogen, in Berlin, he says there's no, the fuel cell, the reason why he wants a fuel cell car is if he parks his electric car on the street, because he has no parking garage in Berlin, he has nowhere to charge it up overnight. And you would have to build an incredible infrastructure to charge all those electric cars overnight. Whereas the hydrogen vehicle, he can fill it up in 5 minutes at a station. So the Europeans have invested very heavily in building out that network.
That's good. So one more question? Victor.
It has nothing to do with the seminar, but with your introduction of David, I'm going to summarize the best electron microscopist, period.
And I could have said that too, so yes, period. So one question from the students. I don't want this to be all faculty-centered. You guys must have doubts,
Great
right?
Are they ready to buy one?
Alex, Lynn, any questions from you? Alex?
We've got one in the front over here. Yep.
Yes.
Why do you think that lithium-ion vehicles were able to be brought to market so much earlier than hydrogen?
Yeah.
Like how early the hydrogen fuel cell was conceived?
So I think you know, the interesting strategy there was, I think in the beginning, you know, every time you want a new technology, if you recognize that the costs are going to come down, and if you're willing to gamble that the costs will come down before you run out of money, then this is going to work out. And I think that was the genius of Tesla, was that that Elon Musk looked at the electric vehicle and said, this has got phenomenal acceleration. It's going to be a great sports car. I don't have to spend a huge amount of money building a complex transmission. So I can charge a lot of money for a sports car and still be able to, you know, I'll still lose money because the batteries are ridiculously expensive, but I'll be able to build up my scale and bring my costs down. So he approached it as, this will be a luxury vehicle, and I can charge a huge amount of money for luxury vehicles, and people will pay for that just because it's a luxury vehicle. And so, whereas GM was like, I'm trying to build a vehicle for the masses, and I'm trying to make it look like my dorky SUV that is trying to compete with the internal combustion engine, and there's no margin to that. So they could have put a car on the market a decade ago if they were willing to lose money on it in order to build market share. And in fact, this is the same story that Toyota had with the Prius. In the Clinton administration had a project on hybrid electric vehicles, and they funded GM. And GM built this vehicle that looks suspiciously like a Prius. And so whenever I visit GM, they'll say, if you want to see the first Prius ever built, it's in our museum in the front of the building at Warren, Michigan. Because they had federal funding to build this vehicle, they were willing to do it. The Japanese saw the Americans investing in hybrid vehicles and said, damn, we got to do that too. So they got the Japanese government to fund Toyota to build a hybrid electric vehicle. Toyota said, I need to get experience with, you know, charging infrastructure and what does it look like on the road. We're going to sell these electric vehicles at a loss, but people are going to get to know them and get to work with them. And that was the Prius. For a long time, the Prius was losing money on every sale, but they were building market share. They were using that to build up their economies of scale, and so they can produce, you know, many, many thousands of these things. And GM, when the Bush administration came in, the Bush administration said, we don't like batteries because the Clinton administration liked batteries. We like hydrogen because it's different. And in fact, it was hydrogen. A lot of the hydrogen came from coal, so you can imagine why that was popular. So they took all the money away from the hybrid project, put it into the fuel cell project. GM said, without the government money, we're canceling our our hybrid electric vehicle. We're going to work on a fuel cell electric vehicle instead, shut the project down, and all the market was left to Toyota. And what became the Volt later on was now 5 to 10 years late to market. So, you know, if GM had been willing to lose money on the early sales so they can get the economy of scale up on the fuel cell vehicle, and then build in and subsidize the hydrogen network until you have enough stations around, it probably would have done just fine. Of course, the trouble is, GM as a brand, would you believe they, you know, you'd have to be able to persuade this was the luxury vehicle. So this is sort of a lesson of, you know, technologies. The first one to do it at scale gets a cost advantage. And it's often hard to overcome that. It takes a long time to do that. That probably both technologies were ready about the same time.
And this cycle continues, right?
Right.
Yeah. All right. Thank you.